All right. Great. So today's lesson, domain in quadratics. This is 2.2.2, triple two. I'm going to kind of break this down on how it relates to parabolas. We'll go into more depth on domain and some other aspects here as we move through the unit. But here we're talking about the domain of parabolas. And first we'll kind of like start to think about what this shape is. And I'll also remind you that domain is talking about the x values. It's talking about the x values as we go in the, no, that's not the button. As we go in the positive direction on the x, all the way towards positive infinity, the laser just keeps going forever. And as we start from the origin here at 0 for x, and we go to negative infinity, all the way forever in that direction. Now first off, can I find the point of negative infinity? Can I find where negative infinity is? No. It's almost a concept, right? It's a concept that it goes forever in that direction. If you really get into a lot of deeper math, you'll see that that's a real interesting area. Calculus definitely talks about the infinity directions. Positive infinity is also not a place you can find. It's a concept. It's just, it goes on forever that way. Okay. So there are some kind of complicated paradoxes in that. But we're going to basically just focus on the domain of these parabolas. As this parabola arches over and comes down, does it just stop right here?
No.
No. What does the arrow tell me?
It keeps going.
It keeps going down and also to the left. Everyone agree with that? Keeps going down to the left. If I followed it down through, along the wall, down through the ground, through the earth, out through our solar system, past through all the galaxies, it would keep going in that direction. Okay. Same for the other side. If we're going in positive, it's going to keep going down forever, and it's going to keep opening up. Okay. It wouldn't make any difference if this was sad face or happy face. If it opens up, it still opens up and keeps going out in both directions. Okay. That's pretty clear just as far as the concept of parabolas. I think we've gone over parabolas quite a bit. So here's the deal with it. Where our values for x along the x-axis, where x isn't time, when we're not talking about time, since they go on forever in both directions and continue to spread out, it always extends to negative infinity and positive infinity for x. It always extends in the negative direction forever and to the positive direction forever. All right, keep snoozing. Great. So for any parabola I have, if time is not involved, my domain, which I just denote here, capital D, colon, is always negative infinity is less than x is less than positive infinity. And I'm going to break down this inequality right now if that's a little confusing still. Don't worry about that. All this is saying, this domain is saying that the domain, which is our x values, goes to the negative infinity forever. It goes to the positive infinity forever because it keeps opening up. Keeps opening up. So we'll just kind of look a little closer at this inequality now. Well, let's see. Who wants to make a fortune in their lifetime? Who wants to be, has a dream to be wealthy? Yeah? Adrian? Okay. So Adrian, when is the youngest age that you want to be wealthy? Like if you said, I want to definitely be wealthy by the time I'm 40. What's your age in your mind? 17? 35? 35? Okay. So would you guys agree that Adrian, if I'm talking about Adrian's age, right here as x, that he can only start to spend his wealth from 0 on. Can he spend his money before he's born? No. So what I'm saying is, Adrian's going to get his wealth when his age is greater than 0. That makes sense? He's going to get his wealth after he's born. And he just said that he wants to make his money by the time he's 35. Let's just look on the right side of this. When x, his age, is less than 35, that's when he's going to be wealthy. Or when x is greater than, it's open towards x, is greater than 0. So the reason we put the inequality in this straight line here is because it tells us where x is located. It's located between 0 and 35. And in this case, he could make all his money on his birthday, so we could put that there. but I'm going to leave those out because when we're dealing with infinity, you can't find that defined point of infinity or negative infinity. It just goes forever. Okay. So this is kind of a little inequality of when Adrian's going to get his wealth. I'm going to hold that to you. If you get it when you're 36, you have to share it. You better be on it. All right, any questions on this? Thumbs up, sideways down. On this general idea, thumbs up, sideways down. Okay. How about for the inequality part? Inequality part, thumbs up, sideways down. Sideways still. Okay, no problem. So we're going to do a couple of these. Don't worry about this. What I'm telling you with this is it's kind of a trick. This is going to be somewhat of a trick question because the answer for any parabola, any quadratic that isn't involving time, is always this domain. So watch how fast I can do this problem. If I have this equation, this function right here, x squared plus x minus 4, just standard form of our quadratics. This isn't involving time, so what is my domain for this parabola? I know it opens up and it keeps going on forever in both directions and up. What's my domain for this parabola? What do you think? My x values. When it opens up, does it keep going towards the negative forever? When it keeps going towards the positive? Forever. So anytime I have a quadratic that does not involve time, I know right off the bat that we have negative infinity less than x is less than positive infinity. That would be my answer. If you ask the domain of a parabola not involving time, that's going to be my domain. If I had it in another form which doesn't phase us, we're okay. We don't have to do anything with this. Right? So if in this case I want to know what my domain is, forget about finding the x-intercepts, which we could find here, but let's just see what this kind of looks like. We know it's A is positive, so it looks opening up. So does it open up and then it stops? It opens up and it keeps going and going to the sides and up, right? The shape of the parabola keeps expanding out and up. So my domain for this parabola, there's no time involved, so it's going to be negative infinity. It's greater than x. It's greater than positive infinity. Answer. Nothing to do, nothing to factor out or really do anything. I'm just talking about the general shape. Since it goes out and down or out and up forever, then this is going to be the domain for any parabola. Okay, Isaac.
Wait, so that's all you have to do?
It's almost like giving a definition of the domain for a parabola.
So all you have to do is find the domain.
For some of these questions, it's going to be real quick and straightforward because that's all they're asking. They say, here is a formula for a quadratic. What's the domain? And again, I look to see that, is time involved? If time is not involved, then it's always going to be this domain. Because it always extends up and out. And it keeps going out to the sides forever. Okay. All right. Any other questions? That was a good question. Not yet? All right. Let's see. Next. This is why I talked about time travel. Warm up always prepares you for this stuff. All right, this is where you have to be careful because the thing is when we deal with models, be careful with the models. Models are just our word problems. Okay, the models are just our word problems. Go ahead and jot that down. Be careful with the models, which is our word problems, because there's no time travel allowed. No time travel. Because, let's look down here at this example real quick. If this is Mr. Casillas kicking the ball, hopefully not kicking the ground or anything, can I see the height of the ball when I'm at negative 20 seconds?
No.
Now I know the ball is going to be in the same place, but when we're talking about models, we're talking about when that action is happening. When I kick the ball, what is my value for my time? Or sorry, before I kick it, right when it's on the ground? What's the time? I haven't kicked it yet. Zero. So within the model, we're always going to start our models at time is equal to 0 because that's when the event starts. If I'm kicking this ball, I really don't care where the ball is at -5 seconds. I want to know, where does it start when I kick it at 0? How high does it go, and where does it land as far as time goes? Okay, so no time travel. When you're doing models, you cannot, you know, a negative value for time isn't going to make sense, because that isn't something that we experience. Models are kind of more related to, they are related to real life. And there's never an instance where we're talking about negative time unless you're time traveling, and no time travel allowed. Oh, it's finishing this. All right, let's jot that down. Slowly finishing that through the day. Now, the next step is we want to find where that object, when the object is on the ground. It's on the ground at 0. It's going to be on the ground over here at some amount of time. Now, the thing is, we want to find the x-intercepts, and if you recall back from factored form of the parabola of quadratics, we make f of x equal to 0. F of x, just the function notation denoting our y value. When f of x, or our y value, is 0, that's where I'm on my x-axis. So what I'm going to do for my steps as far as finding where the object is on the ground, I make f of x equal to 0. And I put it down here again. Just remember to find x-intercepts and make that equal to 0. All right, so where do you think this ball is going to land if I kick it? Maybe here? So to find these places where the ball is when it's kicked and where it lands, I have to see where my y value, my f of x value, is equal to 0, because that's when I'm on this line. And we're going to just kind of break down now, how do I do that? Okay, everybody following with this? Let's see. Yeah. Okay. So no time travel when we have models. That's just the one thing that's slightly different. Okay, who's seen the pumpkin chucker? Anybody seen that on Discovery Channel? What is that? Anybody?
Yeah.
Well, if I'm remembering the correct video, it's where they build a trebuchet and then they have the battle over who can chuck it the farthest.
Yes, it's. I'm not sure it's a trebuchet in this sense. The one I've seen is what? It's like an air cannon. So it
Yeah,
shoots
that
it.
one too.
Yeah, that one's pretty cool. So if I have this air cannon, where does the pumpkin start as far as my time goes? It starts at 0, right? William, can you close that window? I'm getting some glare on my film, or the curtain.
Wow.
All right, I hope that's bright enough. All right, Lawrence, can you open the curtain there that's already opened a bit? Pull that back towards the door. Yeah. All right, that's good. Can't see a vampire. All right, this is how we're going to do it. These are our steps on how we're going to approach models. Okay. With models, we're going to be given a function, given a formula here that's related to the model. When the pumpkin is chucked in the air, it follows this formula in respects to f of x is our height. So f of x is our height as far as our y values. T is our time. In this case, is our x values along the x-axis. So the first step we're going to do, step 1, we're going to make f of t in this case equal to 0. We're going to go into this formula, or this equation, and we're going to do step 1 here, which is make it equal to 0. See, I just took that, made it equal to 0. Because that's telling me that since f of t is height, we're talking about when the height is 0. That's when the ball's on the ground. Okay. So, step 2. Step 2 is to do a little bit of factoring. Okay, so here we're going to factor. Now, what value can I take out of each of these terms? They're connected by addition here. What value can I take out? What's my variable in this case? T. Can I take a t out of both of those terms?
Yeah.
Yeah, because this has a t squared, that has a t. I could factor that out. if I was going for the path of least resistance for this, you could just factor out the t, leave everything else in another expression, and that would be okay. But I'm going to ask you guys to figure out what can I take out of both terms? What's the greatest common multiple I could take out? Or the greatest common factor? 16t. Watch. I'm going to take 0 is equal to 16t. And with factoring, you can do so many different things. You could decide to factor out a -8. You could do whatever you want. Let's take out 16t. What's left over is -t. Plus, what's that going to give us? 1. Okay. So first we factor. So this, in this case, now look, this looks a lot like the warm-up. This looks like a lot like the warm-up where if I'm looking to see what my x-intercepts are, I'm going to make each of those expressions equal to 0. So that's step 3. Let me get rid of this. So step 3, you're going to find x-intercepts. So what I do with this is I'm going to take this 16t and this -t plus 20. I'm going to make both of those equal to 0, just like on the warm-up. So we have 16t is equal to 0. We have -t plus 20 is equal to 0. This is just like factored form of the parabola or the quad. Remember where we just took the two expressions, make them equal to 0. That's going to tell me my x-intercepts. First one's always going to be pretty straightforward. What am I going to get from my first one here? How should I solve for t? 16 times t. All right, we got another situation. You 0 over 16 gives us
0.
All right. So t is equal to 0. And that makes sense because that's where the pumpkin is at the starting point and time is 0. And then over here, how am I going to solve this? How about we minus 20? -t is equal to -20. And then this is really -1 out here. So how do I get to my final answer? I'm going to divide by -1, -1. T is equal to 20. So did this pumpkin chucker, if it at t is equal to 20 seconds, that's where it hits the ground. Is this a really far shot or is this a little shot? 20 what? Seconds. It's in the air 20 seconds. Really far, right? We're talking about maybe a mile. I mean, this is huge. Not that far. Is everybody okay with step 1, 2, and 3 for this?
Yeah.
Raise your hand. What's the crux? What's the hardest part? Number 3? We don't have to graph it. Drawing the model, maybe? Factoring. Okay. If this is hard to factor from here to here, here's the other route I could have gone. I could have said 0 is equal to, I'm just factoring out 1t because I'm lazy. 16t plus 3, 20. I know this t's got to be 0. When I solve this out, I still get 20. This is just the path of least resistance. You can just factor out 1t, and then you have your two expressions. So I think you're going to see that after you start doing these, this is one option, one route you can go. Okay. Next. Next we have the soccer example, and I'll just use this diagram here. We're given this function where h of t is the height again. These should be t's then. Okay. T is time as far as our x-axis goes. Just like in this situation, we have h of t, and we have t, time. So let's do our steps. Step 1, make it equal to 0. Because we're looking for our x-intercepts. Right. I want you to do step 2 and 3. Go ahead and knock those out. We'll come right back. Double check it. All right, let's come back to this now. The situation was this soccer problem. We're given this equation and told that h of t is just the height, t is just the time along my x-axis. My step 1 was to make the function equal to 0, which tells me where it's going to be on the ground. Next, we have to factor this. Somebody tell me what they factored out. What did they factor out? Lawrence.
I factored out 2t.
Okay. So you're saying we'll take 2t out of each of these. What was left over in the first term?
Negative t.
Negative t. And how about the second term?
5.
Plus 5, right? So we factored out a pretty good factor there. There's a bunch of different factors that you could have factored out. You could have pulled out even a negative and switched signs around. You could do a lot of different approaches with this. All right, how about step 3? What are we going to do for step 3? Who feels confident about that? Can lead us through it? Too easy? We make each equal to 0 and we solve it. Okay. Too easy. Sorry, don't want to. 2t is equal to 0. I take this, I make it equal to 0. Negative t plus 5 equal to 0. These are just two equations we need to solve. They're going to be pretty quick. Almost one step for one of them. 2 times t, how do I get rid of the 2 instead of multiply? Divide. So t is 0. Does that make sense? Because at time of 0, the ball's on the ground. I haven't kicked it. Okay. How about this one over here? Jason, how do I get rid of this? Plus 5.
You put onto the side the negative t equals negative 5.
Good. Subtract 5 both sides. We get negative t is equal to negative 5. And then what?
T equals divide by negative 1.
Good. You can divide by negative 1. T is equal to 5. Those are my two x-intercepts. So they were asking where the ball is going to land. It's going to land here at 5. 4, 3, 2, 1. So 5 seconds. That's a pretty good kick. That's a goal kick that goes to the other goal. So that's a goalie, actually. Okay, how are we feeling? Thumbs up, sideways down? Thumbs up, sideways down? Kinda. Rotating thumb. Okay, so I'll let you know right off the bat. I'll go and stop that because it's 22 minutes.